Hello, Math 1224. This is Dr. P with Lesson Launch 16.1, the root of the problem. So in this video, I'm going to give you one of two remaining series convergence tests that we have not yet talked about in class. But first, I want to do a little bit of review of how we might, a couple of methods for determining whether this series here, this series, the sum from n equals 1 to infinity of n times 0.87 to the n, whether that converges or diverges. So you already know actually one method that is very useful in this particular case. Now, before we get started, you might look at that series and think, hey, wait a minute, isn't this just a geometric series? Because I see that there's that telltale constant base raised to a variable exponent piece there, that 0.87 to the n, looks kind of like a geometric series. But in fact, this is not a geometric series at all. It is not a geometric series because I've got this other piece here, this multiplication by n. So if I were to write out the first few terms of this series, I would get 1 times 0.87 to the first plus 2 times 0.87 squared plus 3 times 0.87 cubed, and so on. And there isn't any one constant that I can multiply by each term of the series to get the next term of the series. So here I'd have to multiply by 2 times 0.87, and then here I'd have to multiply by another 0.87, but then I'd also have to multiply by something like 3/2 or something. So there's not a constant ratio between terms in this series, therefore this is not a geometric series. Just wanted to point that out, because sometimes I see students who are tempted to call something a geometric series when all it really has is just some part that looks geometric, but as a whole the series is not a geometric series. Okay, so anyway, what other method might we use to determine the convergence or divergence of this series? Well, we have a couple of options, one of which is to use the ratio test. Let's see whether something like that would work here. Now, sometimes you use the ratio test and it doesn't give you any useful information because we calculate the limit as n goes to infinity of an plus 1 over an, that is the n plus 1th term of the series over the nth term of the series, with the absolute values on there. I calculate that, and if I get something greater than 1, then I'm done. I know that my series is divergent. If I get a limit of 1, then I get no information, and I have to try some other test. And if I get a limit less than 1, then I know my series is convergent. And I know that that limit's always going to be non-negative because everything in there has absolute values around it. So that limit, that sequence term there that I'm calculating is always positive. Anyway, let's see what happens if we use the ratio test on this series. Now remember, the series I was working with was the sum from n equals 1 to infinity of n times 0.87 to the n. So this limit that I'm going to calculate, if I'm using the ratio test, it's going to be limit as n goes to infinity. That's an n, not an m there, of an plus 1 over an, and that's the limit as n goes to infinity. And my tablet penmanship has gotten really bad over the break. It's like I'm starting over practically here. It's n plus 1 times 0.87 to the n plus 1. And as usual, I'm dropping the absolute values because I know that everything here is positive anyway. Absolute values wouldn't affect that. So that's going to give me the limit as n goes to infinity of n plus 1 over n times, and I think this part here, 0.87 to the n plus 1 over 0.87 to the n, that's going to simplify to 0.87. So now I'm just looking at the limit as n goes to infinity of n plus 1 over n times 0.87. And this ratio here, as n goes to infinity, that goes to 1. Some of you have left really good justifications for things like this on your homework and on your exams. This would be the same as the limit of 1 plus 1 over n over 1, because you can divide the numerator and denominator by n. Anyway, I've still got that 0.87 there. And as n goes to infinity, that first part is just 1. So this limit is just 0.87, and that is less than 1. Now I'm going to model here how you should write out the solution to one of these, because it's not just a matter of calculating a limit saying, oh, I'm done. You have to say what all this means. So we know, there we go, that the limit as n goes to infinity of an plus 1 over an is 0.87, which is less than 1. And that less than 1, that's the part that we're really keying in on here. So because that's less than 1, we know by the ratio test, the sum of the a sub n's from n equals 1 to infinity, that sum converges. And you might even go ahead and do the polite thing, which is to write out what it is, the series that you were trying to investigate in the first place, n times 0.87 to the n. That series converges. There we go. Anyway, you get the idea. That's one way to determine the convergence of this series. Now there's another one, which at first it's a little bit of a pain because there's a couple of things that you have to know in order for this test to be a useful tool. But once you know those things, it can make some of these tasks a little bit easier. And that test is called, get a different color here. Let's see. Yeah, I'm going to invent a new color. Just a second there. Let's use a nice dark green for this. Beautiful. Okay. This one's called the root test. So you get it green because plants, roots. Anyway, sorry, sense of humor is a little rusty after a whole week off. Anyway, this is called the root test. The root test says this. The root test, like the ratio test, is a theorem about series. It says consider, I know there's that word consider again. Consider the sum from n equals 1 to infinity. The starting point's not really that important. It could start at 0 or 2 or someplace else. But consider the sum of these an's, okay? Are you considering it? All right, good. Suppose we evaluate the limit as n goes to infinity of this, of the nth root of the absolute value of a sub n, okay? All right, so in other words, we're looking at the magnitude of a sub n and taking its nth root, the nth root of the nth term of the series. All right, so again, there's a few conditions here. Actually, let me just write it this way. Let me just put it in separate bullet points here. There we go. Okay, bullet point 1, number 1. If this limit exists, and is less than 1, the series sum of a sub n equals 1 to infinity, this series converges if that limit is less than 1. Okay, that's condition number 1. Number 2, if the limit is greater than 1, or the limit goes to infinity, make that a little bit clearer there, goes to plus infinity, then the sum of this series diverges. Okay, if that limit's greater than 1, that is this limit here, the limit of the nth root of the magnitude of the nth term, if that limit's greater than 1 or goes to infinity, then the sum diverges. And once again, you've probably seen this coming now. If the limit exists and is equal to 1, then the root test provides no information. Which means if you want to determine the series convergence or divergence, you're going to have to use some different test. All right, so that's the root test there. Now let's use that and see if we can use that as a tool to determine whether that series from earlier converges this sum from n equals 1 to infinity of n times 0.87 to the n. All right, so I'm going to start over here. I'm going to look at this series again, a sub n equals n times 0.87 to the nth. And I'm going to calculate the limit. I'm going to call that L. The limit as n goes to infinity of nth root, absolute value, a sub n. Again, the absolute value, not really important here because everything here is positive. Nth root of n times 0.87 to the n. All right. Now, this time I've got a little work to do here. A little work to simplify this. Now, first of all, one thing to remember is that taking any kind of root, square root, cube root, nth root, that distributes over multiplication. It does not distribute over addition. If I had n plus 0.87 to the nth here, I could not do what I'm about to do here. But nth root does distribute over multiplication. So I get nth root of n times nth root of 0.87 to the n. And as you probably already figured out, that nth root of 0.87 to the n, that's just 0.87. And I've got this nth root of n, which I could rewrite as n to the 1 over n. So it feels like everything here is going to rest on what happens with this dude here. What is the limit as n goes to infinity of n to the 1 over n? So I'm going to ask that as a separate question here. What is that limit? And I'm going to do this here so that if you run into this problem in some other task, or you run into this issue someplace else, you can just say, oh, by the way, one time we found that the limit of n to the 1 over n was this, and you don't have to calculate it again, because this is just a good one actually to know. Just know off the top of your head, because it comes up so very often when we work on these problems. All right, so what is the limit as n goes to infinity of n to the 1 over n? Well, if I just try to calculate directly using my number sense, I have a base that's going to infinity and an exponent that's going to 1 over infinity. 1 over infinity is like going to 0. That's an indeterminate form there. And it's not even the kind that I can use L'Hopital's rule on because it's not in the form of a fraction, at least not yet. So what I'm going to do is I'm going to call that limit m, and then look at the natural log of m. The natural log of m is going to be the limit as n goes to infinity of the natural log of n to the 1 over n. And then that's the limit as n goes to infinity of 1 over n times the natural log of n. All right, because I'm using properties of logs to move that this exponent out as a multiple of this logarithm here. And now look at that. Now I have this in the form of a fraction. Limit as n goes to infinity of natural log of n over n. And that's a fraction. You'll notice the top and bottom, numerator and denominator, both are going to infinity, which means now I can use L'Hopital's rule and rewrite that as the limit as n goes to infinity of 1 over n, that's the derivative of the numerator, over the derivative of the denominator with respect to n. And that's just the limit as n goes to infinity of 1 over n. So this natural log of m here from earlier, that's equal to 0. If the natural log of m is 0, then that means that m is e to the 0, which is 1. The moral of all of which, I know that this has kind of gotten into a long tangent here, but the point of all of that is that we now have a theorem that the limit as n goes to infinity of n to the 1 over n, that's 1. And you can now use that fact anytime that you want to. You don't have to reprove it. Although I'd be impressed if you showed that you were able to do that, because it's kind of a nifty little calculation there. You have to go through a few different steps and reasoning about limits in order to do that. But anyway, now we know that the limit of n to the 1 over n is 1. So now I go back to where I was doing the root test earlier. Remember, that's where all this came from here. And now I know, based on this theorem, that that limit is 1 times 0.87, and that limit is therefore 0.87. So now I know, just put my conclusion up here, so now we know that the limit as n goes to infinity of the nth root of absolute value of a sub n is 0.87, which again, important part, it is less than 1. Therefore, by the root test, the sum from n equals 1 to infinity of n times 0.87 to the n that converges. Shouldn't surprise us, we found it converges earlier, so hopefully we're not going to get a different result now using a different test. But anyway, it's nice to know that there's another way of getting there. So that's called the root test. And the way that it works, I don't want to spend a whole nother 5 minutes on what's now a 15-minute video explaining why it works. But I do want to say a few words. I don't like throwing theorems at you and just, having this be another fiat about how we determine series convergence or divergence with no reasoning behind it. The essential reasoning behind this is, you'll notice here we're getting a limit of 0.87. What that's telling us is that this series here, the series a sub n, is eventually behaving kind of like a geometric series with common ratio 0.87, which we know from the geometric series test, that's a convergent series. Now, when I say eventually and kind of like, I'm really fudging quite a bit there, because I did say earlier, this series here, the one that I wrote at the beginning, that's not a geometric series. This factor of n creates kind of a fudge factor that takes it away from being geometric. But there is a little bit of real analysis that you can do. Real analysis is sort of like calculus with actual proofs behind it, mathematical proofs behind the theorems. You can do a bit of real analysis and show that, okay, this is actually a little bit bigger than a geometric series with common ratio 0.87, but eventually it will be smaller than a geometric series with common ratio 0.88, for example, or 0.872. You could pick any ratio, and eventually this will be smaller than a geometric series with that ratio. And a geometric series with that ratio still converges, so this one has to as well by basic comparison, or by limit comparison, whichever you like. Anyway, that's the idea of the root test. It's just another one of these where you grind out this calculation here, and sometimes you run into some object like this that takes a little bit of further study. But now you know that n to the 1 over n goes to 1, and so you can use that any time. That might make the root test easier to use in some cases. Okay, that's it. Now we're on 17 minutes. So I'm going to stop there, and the next video will be the other series convergence test that I need for you to know before we march on into the next chapter. All right, stay tuned.